All right. If you got your homeworks, turn them in. Okay. Go for it. Yeah. Wow, these homeworks look amazing. So excited. Yeah, perfect. Thank you. Thanks. Should be one over there by the sink. I don't know why there's one by the sink.
Because that's what you do when you wash your hands.
Yeah.
Stay them together.
Yep. Thank you.
Would you by any chance be able to cover 24?
Sure.
Like whatever.
Did I really give you a question like 24?
It's 2022.
Alright, I think oh yeah, implications. All right, so 24 says, let P of n be the proposition n is less than 2, and let Q of n be the proposition n squared is less than 5. Everybody turn in their homework? Over by the sink. So P is the proposition n is less than 2. Q is the proposition that n squared is less than 5. And it asks, are they equivalent and does one imply the other? Thank you. So saying two propositions are equivalent, thank you, means that they are true or false together, right? If one is true, the other is true, and vice versa. So the first part of the question is over the integer z. So over the integer z. If n is an integer, if it's less than 2, is its square less than 5? What do you think? Not necessarily. What's a counterexample? -3, right? That's less than 2. N squared is not less than 5. So they're not equivalent, right? P is not the same thing as Q. Does one of them imply the other? So what does this mean? If P is true, is Q necessarily true? This means P implies Q. So if n is less than 2, is n squared less than 5? Well, we just said no, because -3 is less than 2, but its square is bigger than 5. So P does not imply Q. Does Q imply P? If n squared is less than 5, do we know that n is less than 2? What's a counterexample?
2.
2. 2 squared is less than 5, but it's not less than 2. So that's also no. So yeah, they're not equivalent, and one does not imply the other. And then, hey, part B, what about the natural numbers? So part B is over n. So naturals, I believe in the book, are 0 or positive. And so if n is 0 or positive, are P and Q equivalent?
Yes.
No. No? What's the counterexample?
Q would still be a counterexample.
But 2 is not less than, yes, so 2 squared is less than 5, but 2 is not less than 2. So they're not equivalent. But P implies Q, right? And that's easy to prove because n is a natural number less than 2. It's either 0 or 1. We only got 2 cases, and we can check each case. 0 squared is less than 5, 1 squared is less than 5. So yeah, if P is true, we can absolutely say Q is true. But again, Q does not imply P because n squared could be less than 5 when n is 2, but in that case P is not true. So that's a case where Q is true and P is not. Cool. Other questions?
Could we do one like story like the paragraph one?
Yeah, do you have a number?
I can't forget the number.
I don't remember what I assigned, so I'd have to. Which one? Let's see.
3.8.
Yeah, 3.8.
3.810. Use quantifiers to say that the equation a plus x equals b has solutions for all values of a and b. Is that a good one?
So no.
I think it was
The one with like one
yes,
yes,
sir. Yeah, I think it was like this. 22.
Oh, Professor Smooth Talker or something?
Control S.
22, Professor Smooth Talker makes the following promise to his class. If you receive an A in the course, you are happy. You will do all your assignments, or you are not happy if you concentrate too hard. Well, you will not do all your assignments. Therefore, if you're happy, do not concentrate too hard. What the heck does that mean, man? Let's find out. All right. So each of these promises is a declaration, so it's going to be a proposition. If you receive...
Dismiss this out of hand, because the last one isn't even a proposition. It's an imperative.
If you are happy...
Do not concentrate too hard. That's the way I answered it, but so you guys ignored everything else because it's not even testable. It's not a proposition.
I don't know if that's the intent, though, but you're right. I'm guessing this means if you are happy, you do not concentrate too hard.
Okay.
But that's
I wasn't sure
badly
how technical
worded.
to take it. 'Cause
I don't think it's supposed to be a trick. There are some things in this text that don't quite make perfect sense, but I think they're from looking at the answers of those where they have answers, I think they're intended to make sense. So I think this is if Professor, if you are happy, then you do not concentrate too hard. But let's try that and see if we can make sense out of this. So again, we're going to try to make a logical argument in propositional calculus, but usually the prescription is to try to make your propositions as small as possible. We could make a proposition for this entire thing and then ask if that proposition is true, but we can't really get very far with that. So instead of making a proposition that if you receive an A, you are happy, I'm going to break that into a pair of propositions. So let's say A is the proposition that you receive an A. And H is the proposition that you are happy. And this first statement is if you receive an A, then you are happy. So I'm starting to translate this. A is the proposition you receive in A, H is the proposition you are happy. If A, then H. Please, when you're doing this, though, actually say A is the proposition you receive in A, H is the proposition you are happy. Because if you write colons, eventually those colons turn into equal signs, and then those turn into mathematical equalities, and then everything goes haywire when we get into proofs about numbers. Okay, you will do all your assignments or you are not happy. So let D be the proposition. You do all your assignments. And so the second statement is you will do all your assignments or you are not happy. So it's either D or not H. So that's our second piece of the professor's statement. If you concentrate too hard, you will not do all of your assignments. So C is going to be the proposition that you concentrate too hard. And so this third statement is, if you concentrate too hard, then you will not do all of your assignments. So C implies not A. And then the conclusion says, if you are happy, which is H, then I'm going to say you do not concentrate too hard. H implies not C. So now we've hopefully translated this into an equivalent theorem, and we want to know if it's true or not. So without getting into symbolic syllogisms and all of these fancy sounding terms, just thinking about this, anybody have a gut reaction to this as to whether it's going to be valid or not? No? That's a good answer. Oh, it's not going to be valid? Okay.
Yeah.
I thought you meant you didn't have an instinct. Okay. How many people kind of feel like it's not going to be valid? How many people feel like it is going to be valid? Okay. So if I feel like this is valid, I'm going to start off trying to prove it. If I feel like it's not going to be valid, I'm going to start thinking about some of these implications and see if I can find a contradiction. And just kind of thinking about it, first thing is D is a red herring, right? It doesn't pop in anywhere else. It really does no good for us. It doesn't tell us anything about H or not H. So that second statement just seems like it's thrown in there just to distract us. So I'm kind of going to ignore that, right? And now I've got a pretty simple set of propositions. Well, A implies H, C implies not A, H implies not C. Well, if H is true, C is false. That doesn't really get us anywhere. If A is true, H is true, and if H is true, C is false. And that doesn't do us any harm. If A is false, this doesn't tell us anything, but it tells us C could be true. And if C and H are false, then this tells us that C could be false. So I don't see any problems in here. Do you have an instinct why it might not be true, or
Oh, just the phrasing of the question.
just the phrasing of the question? Okay. So let's try and prove this. So let me number these first three things and say these are hypotheses. I'm being really sloppy here. Don't do this. But I'm rewriting my question and turning it into the first three steps of my proof and saying those are hypotheses. And I'm going to, not part of proof. All right. Well, A implies H. C implies not A. D or not H. Anyone got any ideas? Yeah.
Isn't it the third statement is C implies not D instead of not A?
Oh, that would be nice. If you concentrate too hard, you will not do all your assignments. Thank you. Okay, that's totally different. Okay, C implies not D. Thanks. All right, so this second statement is part of the argument. Well, ideas?
Take as much positive of 2 or 3 or 2 and 3.
Cool, cool. So I'm going to clean this up a little, prove that H implies not C. I'm going to take this out of here. But in my brain, I want to make a statement about H. Well, contrapositive of, not contrapositive, but 2 is telling me something that might turn into something about H. Contrapositive of 1 will tell me something about not H. Contrapositive of 3 will tell me D implies not C. So let's do that. So if D, then not C. So there's something we can do that can get easily overused, but there's something called conditional equivalence. And conditional equivalence basically says if P then Q is logically equivalent to Q or not P. It's a way to change an if-then into a disjunction, or to change a disjunction and or into an if-then. And we've got an if-then, we've got an if-then, we've got an or sitting out here. I suspect if we change that into an if-then, we might be able to change something or do something like that. So D or not H should be the same thing as H implies D. And that's conditional equivalence of 2. Right? This is saying that an if-then is true if the conclusion is true or the hypothesis is false. So D implies not H will be true if the conclusion is true. In other words, H implies D will be true if the conclusion is true, meaning D, or the hypothesis is false, not H. So what can we chain together now? Chain rule. What do we want to chain? H implies D, D implies not C, H implies not C by the chain rule. That's what we're trying to show. So that looks like a valid argument. Phrased in an invalid way. All right, so I'll get this graded hopefully by Friday and back to you, and if I see specific things, we'll talk about those. Any other questions? All right, so let's talk a little more set theory. So I want to talk about something called membership tables. And we've been talking about properties of things like unions and complements and intersections. And we saw some identities related to these, I think. Like, for example, A union B is the same thing as B union A. Right? We saw that, or I claimed that De Morgan's theorem was still true. And we can actually prove some of these things using a membership table. So let's prove a property called absorption. This is a useful theorem sometimes. It basically says A union A intersect B is equal to A. Well, what does that mean on a Venn diagram? Here's a set A, here's a set B, here's their intersection. It's saying if we take A and we add in the part of A that overlaps with B, we should just get A. Well, it kind of looks right on this particular Venn diagram. And it may ring as being true, or reasonable at least, because A intersect B is things that are in A and in B simultaneously. And if we take A and we just add in some more things that are already in A, we should just end up with A. So this is probably somewhat plausible at least, but we can prove that this is equal using this mechanism of a membership table. So here's the idea. You've never seen anything like this before. I'm going to make a table. I'm going to list columns for A and B. Now these are sets. And there's some universe that we may not have specified, but there's some universe of elements from which A and B come. And there's things in this universe that may not be in A and B. So A could be, the numbers 1, 2, 3. B could be the number 2, 4, 6. And the universe might be all numbers plus zoo animals, right? But here's the thing. If we pick any element in the universe, it could be a member of A or not. It could be a member of B or not. But there's only 4 possibilities. One possibility, it's not a member of A. It's also not a member of B. And I'm going to represent that possibility by writing a 0 under A and a 0 under B. And it says this element is not in A and it's not in B. Or it could be that the element I picked is not a member of A, but it is a member of B.
Oh, no.
Or it could be a member of A, but not B. Or it could be a member of both A and B. And those are the only 4 possibilities. So I'm writing down 1s and 0s, and any element that I pick, exactly one of these cases is true. Well, we know what a union is, right? A union is the set of all things that are in A or in B. So if I pick any element in the universe, suppose it's not in A and it's not in B also, so it's in neither of those, is it in the union? No. Suppose that element's not in A, but it is in B, is it in the union? Right? The union just says it's in A or B, and since it's in B, it's definitely in the union. And if it's in A, that's enough to say it's in the union. Suppose it happens to be in both of those sets, is it in the union? Absolutely. So there's a membership table for a union operation. How about the intersection? Intersection means it's in both A and B. So if it's not in either, it can't be in the intersection. And if it's not in A, or if it's not in B, it can't be in the intersection. But yes, if it's in A and B, it's in the intersection. This is another duel between, 250 and set theory. What about the complement of A? If our element does not happen to be in A, is it in the complement? Well, the complement is a set of all things not in A, so yeah. And if it's in A, is it in the set of all things not in A? No, it's not in those. So there's the complement. And just for completeness, there's the complement of B. So yeah, these truth tables from 250 work for set theory. Yes. So let's look at our absorption theorem. We already have a column for A. We have a column for A intersect B. Let's make a column for A union A intersect B. And that's just the union of this column with that column, which we now just think of as an OR. So what's the OR between these two columns? 0, 0, 1, 1. And guess what? This set operation has exactly the same membership properties as A. And that's enough to say that this set is equal to that, because what does it mean to say two sets are equal? Something belongs to this set if and only if it belongs to that set. All right, so those are equal. Hopefully this freaks you out a little bit, right? Because when you were doing engineering 250 and building circuits on proto boards and wires and all that stuff, you probably were not thinking about sets and unions and intersections of sets, but you were. So that's kind of cool. All right, so that's membership tables. And these are great for computers because computers can tell you all kinds of things about sets and set operations now just by doing Boolean algebra. It's absolutely not the last time we're going to see Boolean stuff popping up in here. Okay, if we order the elements in the universe, a first element, second element, third element, we can use that to represent sets very nicely in computers with binary strings. So suppose we have a set consisting of A, B, C, D, E, and another set consisting of A, E, I, O, U. So let's call this set X, and let's call this set Y. And suppose our universe consists of 26 letters, and I order these first, second, third, fourth, 26th. So I'll put some cheats up here. E is 5, I is 9, O is 15, and U I think is 20, 21. And A is 1. Well, if we have 26 things in our universe, we can make a 26-bit string to represent any set. And we do it as follows. I'm going to start from the right, and I'm going to write down a 1 if element 1 is in my set and a 0 otherwise. So element X is going to look like this: 1, 1, 1, 1, 1, 0, 0, 0. Oh, I didn't leave enough space. There's element X. And say again? So I'm writing down 26 bits. This first bit tells me if the element that I've called element 1 belongs to X, which it does because element 1 is A. Element 2 is B. B belongs to X, so I'm putting a 1 here. Element 3 is C, so I put a 1 in the third position. Element 4 is D, put a 1 in the fourth position. Element E is in the set, so I put a 1 in the fifth position. The sixth element would be F, and that's not a member of X, so I put a 0 there, and all these other bits are going to be 0.
So it's from right to left.
So I'm just doing it from right to left, just for fun. You can do it either way you want. So my set Y would be the following. It would have an A, no B, C, D. It would have an E, F, G, H. It would have an I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. So a 26-bit string represents any possible set. So how many possible sets are there if I can represent any set with 26 bits? 2 to the 26th. So there's 2 to the 26th possible sets. Well, every possible set is a subset of the universe. So there's 2 to the 26th subsets of the universe. In other words, the power set of the universe contains 2 to the 26th sets. That's a tongue twister. And we've already seen that the number of elements in some set should be just 2. Sorry, the number of elements in the power set of a set should be 2 raised to the number of elements in the set. So this still makes sense with what we did a few days ago. And if I want to find the intersection of these, I can take the logical AND of these two bit strings. If I AND 1 and 1 is 1, 1 and 0 is 0, 1 and 0 is 0, 1 and 0 is 0, 1 and 1 is 1, and all these other numbers, I'm going to get zeros. And guess what? That bit string corresponds to the set containing just A and E. That's the intersection of our two sets. And of course, what happens if I OR them? I get a 1 anywhere that there's a 1 in either. And that's going to be the same bit string that you would get if you looked at X union Y. And last but not least, what do I get if I take the complement of one of these strings, change the 1s to 0s and 0s to 1s? You get the bit string corresponding to the complement of the set. And these are things computers just chow on. Very easy to do these operations inside a CPU. Let's talk about cardinality. Cardinality of a set is a measure of how big a set is. It's a measure of its size. And if S is finite, meaning it has a finite number of elements, then its cardinality equals the number of elements in the set. And the cardinality is just written as S inside vertical bars. So for finite sets, cardinality is the number of things in the set. But that's not actually how cardinality is defined. Yeah?
I was gonna ask you that. What does cardinality represent if it's not finite set?
Yeah, that's going to take about a half hour, but it's a good trip. So let me give you a definition first. Two sets, not necessarily finite. S and T have the same cardinality. Meaning vertical pipes of S equals vertical pipes of T if the following is true. If there exists a function from S to T which is what we'll call one-to-one and onto. All right. We'll talk another time about what exactly one-to-one and onto means, but just think of it as a one-to-one correspondence. So if this is our set S, and this is our set T, and these are the things in S, and these are the things in T, we can find a function which maps each thing in S to exactly one and only one thing in T. And when we're done, everything in T has been mapped to from something in S. So it's a one-to-one correspondence.
It's also injective and surjective.
It's also injective and surjective, which is bijective. So a one-to-one is injective, onto is surjectives. Exactly. So the easier way to think of this is, you know, here's a set S, here's a set T. Give me an element of S, I'll give you an element of T. Give me another element of S, I'll give you another element of T. And you can pair these things up without overlapping and without missing anything. So when you're done pairing, you don't have anything left over in T that you haven't paired with, and you don't have anything in T that you paired with two things in S. It's a one-to-one. One thing in S goes to one thing in T. And if you can come up with such a mapping, then we can say those two sets have the same cardinality. And if our sets have a finite number of elements, this means exactly the same as they have the same number of elements. 12 elements here, 12 elements there, you're guaranteed you can make this one-to-one association between elements here and elements there. Just put some ordering on them. Take the first element here, first element there, pair them together. Second element, pair them together. 12th element, pair them together. So these are equivalent definitions. This is the way we think of things as having the same size. They have the same number of elements. But we formalize that by saying there's this one-to-one association between the elements of each set. This has the advantage that this definition will extend to infinite sets. Because we can make mappings between infinite sets just as easily as we can make mappings between finite sets. For example, the positive integers and the negative integers both have an infinite number of things in them, but it's really easy to come up with a one-to-one mapping of integers bigger than 0 with integers less than 0. Right? What would such a mapping be? Take x over here, take negative x over there. It's a perfect one-to-one mapping. So the set of positive integers and the set of negative integers have the same cardinality. All right, so this leads us to story time. So this is the story of a mathematician from 1800s, early 1900s, named David Hilbert. And Hilbert was a giant of mathematics. This part of the story is true. He really shaped a lot of mathematics at the end of the 1800s. He trained numerous students. If you look at a who's who of the great names in mathematics, they can often be traced back in their lineage to David Hilbert. He was their teacher, or he was the advisor of somebody who became the advisor of somebody amazing, right? He was just all over the place. So at the end of the 1800s, right, turn of the century, everybody was really excited. New century, the 1900s, it's incredible. We're going to do amazing things in the next 100 years. What are we going to do in the next 100 years? And so David Hilbert set about proposing a set of guidelines for where mathematics might go in the next century. And he came up with a series of problems, about 24 problems, that he suggested mathematics work on. And these are just called Hilbert's problems. And there's a number of these that have been solved. There's a number of them that remain unsolved. But the exploration of these problems has led to the development of numerous fields of mathematics, and in some cases caused great upheaval in fields totally unrelated to the original problem. So this was a really wise set of problems to work on, good exercise set. A homework set that took, 100 years and still isn't finished. So that's David Hilbert. Okay, so now we go into the part of the story that might not quite be historically accurate, which is David Hilbert eventually burned out on mathematics. He got tired of working at a whiteboard. He wanted to interact with more people, so he decided to go into the hotel business. And he decided he was going to open a hotel at the edge of town. He was living in Switzerland somewhere, and bought some property, and there was a building on it, and he fixed it up and decided he was going to open a hotel. And this was just called Hilbert's Hotel, and he figured people probably know my name, they might come and stay. Well, opening day, there was a big line all the way down the street. Everybody wanted to stay at Hilbert's Hotel because this person was famous, and the hotel sold out, in a matter of minutes. And the next day, same thing. This went on for a few weeks, and some people started to leave because they had to do other things, and other people would come in. Hotel was sold out every night, and he started thinking, I might be onto something here. I should make a bigger hotel. So he added another wing, and he added another 20 rooms, and it was still sold out every night. And he was making a lot of money because, so many people were staying at the hotel, and he could raise the prices, and they'd still keep staying at the hotel. And as he got more money, he kept expanding. And soon the hotel had 100 rooms, and then 1,000 rooms, and then 1,000,000 rooms. And he kept making it bigger and bigger, and it kept filling up every night. And eventually, he expanded the hotel so far that it had an infinite number of rooms in it. Okay. So what does it look like when a hotel has an infinite number of rooms? Here's what that means. It means there is a door right next to the front desk with room number 1 written on the front. And right next to that is a door, room number 2, and not surprisingly, next to that is room number 3, and it goes on. Now, there is no door with the room number infinity written on it, because that's not a number. But to say that there's an infinite number of rooms means that if you pick any number, 1, 4, 7, 3, 6, somewhere there's a room with that number written on the front, and there's at least one more room to the right of that. In fact, there's an infinite number of rooms to the right of that. But for this to be an infinite number of rooms, all you need is the property that any number that you think of bigger than or equal to 1, there's a door with that number on it, and there's more rooms beyond that. That's what it means to be infinite. 10 gazillion, 590,000, there's another room to the right of it.
Does that mean there's number 4?
Well, I'm coming to that. All right, so we got the idea, right? Infinite number of rooms. Okay. So Hilbert's having a good time. He's got his infinite hotel. Hilbert's Grand Hotel, it was called. And one day his friends decide, Hilbert's birthday is coming up. We should throw a party at his Grand Hotel. That would be really cool. Okay, so they start making plans for this party at Hilbert's Hotel. And they start sending out bulletin board messages, because there was no internet yet. But bulletin board messages saying, party at Hilbert's Grand Hotel, such and such a date. And everybody's excited about coming to this. And everybody in the world, which was a few billion people at the time, decides they're going to come to this party. Okay? not a problem because there's way more than a few billion doors. There's an infinite number of doors. Okay. Now, the weird thing is that there was a group in Geneva that was exploring parallel universes, and they were trying to open portals to parallel worlds. And at the moment that they got the invitation to Hilbert's party, and one of them read it out loud, they had inadvertently opened up a doorway to every parallel universe out there, an infinite number of them. And somebody heard that in each of these worlds. And so there were an infinite number of people, one from each of these universes, that found out about the party and transported to our universe and decided to drive down and stay at Hilbert's Hotel. So the night of the party, an infinite number of guests showed up. And they all came to the front desk and they said, you know, we'd like to stay at the hotel overnight. And the front desk clerk, very skilled at their job, you know, was like, no problem. He started handing out keys and everybody got a hotel room, okay? Well, that's not a problem because an infinite number of guests, we can think of those guests as being, you know, guest G1, G2, G3, G14,736, and so on. And you just associate each guest with each room. And it's very easy to put each of these guests in the rooms. The hotel is completely full. Everybody's got a room. Nobody got turned away. Okay, you got the setup? All right. Now, party's in swing. It's about 10 o'clock at night. But one of Hilbert's graduate students who had been going to the party had car troubles, and their car broke down about 10 miles outside of town. And, you know, the mechanic was planning to go to the party, so they were trying to get out of there and so on. So it took a long time to get his car fixed. And eventually it was repaired, and they rolled into town, and they came to the hotel, but the hotel was already completely full. Parties in swing, music, cake, all this kind of stuff. He goes up to the front desk anyway, and he says, you know, I'm really late, but I'm was one of Hilbert's students. I really, really want to come to the party and stay at the hotel. Is there any way you can fit me in? And the clerk says, give me a minute. And he reaches under the desk and he pushes a little button and he hands the person a key and says, here's your room, enjoy your stay. So here's the first question. The hotel was infinitely full with an infinite number of guests. How did the clerk find room for this new guest to come in without kicking anybody out or forcing anybody to share a room?
He gave them the janitor's closet.
And a refund. He did not give them the janitor's closet.
Like an arbitrary room. Everyone in the level afterwards, just forward their room.
Oh, say that again?
So he picks an arbitrary room, and every person after that arbitrary room picked and moved forward 2 rooms, there's 2 more spaces.
There you go.
Oh, it's on these lists.
Right? So the clerk could give them the key to room 1 and hit this little button under the desk, and a room lights up in each room and says, sorry for the inconvenience, please move down 1 room. And each person gets up and moves down 1 room. Now room 1 is empty, and that's where the new guest goes. So what just happened? Infinite hotel, infinite number of people, every room filled, but you can still add 1 more person. Well, that's a little weird, but it works.
Wasn't it supposed to say it can be full in the first place?
Oh, it's full in the sense that if you looked in any room, you'd see a person who had checked in there. So room 10 gazillion had somebody sitting in there. That was guest 10 gazillion. Room 17 had guest 17. Well, now room 17 has guest 16. But still, every room has a guest in it. But we got an extra guest in there. And that's kind of magical. That's why the clerk was well paid. Because they could make things like this happen. Well, in some sense, the set of guests before this extra person showed up has the same size as the set of guests after the person showed up. Because each of those sets of guests can be put into this one-to-one association with the set of rooms. And therefore, they can be put into one-to-one association with themselves. So this infinite set, or this infinite set with this extra guest late added to it, are the same size. They have the same cardinality. Even though your brain is insisting they have different numbers of elements in them, but they're both the same size in the sense that they're both infinite.
So, taking it a couple steps back, if the hotel only had like 10 rooms, but only 5 people were in it, and there were 5 rooms filled, then they wouldn't have the same cardinality because the guest's cardinality would be 5 and the hotel's 10?
Right, exactly.
Gotcha.
And if there were only 10 rooms and there were 10 people in there, then you couldn't do this trick of move down because the last person wouldn't have a place to go. But homework question, for any integer x, there's an integer y bigger than x, right? Right there. For any room, there's a room to the right. All right, so that's a little bit weird. Guest showed up. All right, well, the party's going on. Everybody's happy. Everybody's in there. And around midnight, some people make a realization, which is Hilbert had a second hotel. It was called Hilbert's Not Quite as Grand Hotel, and it was on the other side of town. And it also had an infinite number of rooms, but the rooms were a little smaller, and the ceiling fixtures weren't as elegant. But some people stayed there anyway because it was a little less expensive. So when people got their invitation to the party at Hilbert's Hotel, an infinite number of them actually thought it was the lesser hotel across town. And they're hanging out, you know, and they're having a good time talking, but there's no music, there's no band, there's no food. And eventually they start to notice that there's all this noise coming from across town, and they figure out, we're at the wrong hotel. So now an infinite number of people come across town, go up to the front gate and say, we would all like rooms at your hotel. Do you have space for us? And the clerk says, sure, give me a minute. And reaches under, presses a different button, starts handing out keys, and now this infinite number of guests from across town each get a room, and everybody's got their own room, nobody got kicked out, nobody has to share. So how did that happen? How did the clerk get in an infinite number of new guests to this room, to this hotel that was already filled up?
Was it simultaneous?
Yeah. Don't worry about logistics of handing out an infinite number of keys.
Well, yeah, I know.
So you have the previous infinite group along with the new infinite group?
Mm-hmm.
Could you just do what you did before over and over and over again?
Yeah. Just
But you'd have to do that, and that would work, but you'd
No,
have to
take-
do it an infinite number of times.
But it did a finite number of times.
Right, but if you had to keep doing this, right, you would never finish the process.
So he finitely added an infinite number of people.
Yeah.
He just expanded into negative numbers of rooms.
You could construct an infinite number of rooms really quickly, but no. But you're thinking in the right direction.
You have this every other Christian.
Something like that. Where would you move them to?
Could you just double every person in this room? Or at least the odd ones, and then put them all in odd.
Ah,
Odd ones?
okay.
Well, yeah, you could have one infinite group of odd and another infinite.
So let's have whoever's in room 1 move to room 2, whoever's in room 2 move to room 4, whoever's in room 4 move to room 6. And we can do this, right? Whoever is in this room can move to a room with twice the room number. We know that room exists because there's an infinite number of rooms. And you can probably satisfy yourself that whatever room you happen to be in, there's a place for you to go, because you can go into the room with twice that room number. And whoever had been in that room has already moved to another room. But after everybody has done this shuffle, all the odd number rooms are available. And you got an infinite number of those. That's where you put the new guests. So we had an infinite set of original guests. And we won't say it equals infinity, but as a shorthand, I'll say this was an infinite set, right? And we had a collection of new guests, which was also infinite. And when we took their union, we got an infinite set. But this new set had the same cardinality as the original set, and the same cardinality as the set of people from the other hotel. And our brains want to tell us this set is twice as big as the original, right? Every element that we had in the original, now we got 2 elements in there. How can it be the same size? For finite sets, that intuition is perfect. If we had 10 elements, now we've got 20, the set's twice as big. For an infinite set, that intuition fails. Because even though this seems like it has twice as many sets, this can be put into a one-to-one correspondence with the original set. So the cardinality of this bigger set is exactly the same as the cardinality of the original set. So that's a little weird too. And we can do this 3 times, 10 times, 1,000,000 times, and we can just keep doing this trick. So we could fit in any finite number of these infinite sets of guests and still squeeze them into the original infinite set of rooms. All right, so the next town over, there was a hotel called Blauman's Hotel. And Blauman's Hotel was also very grand. And in Blauman's Hotel, the rooms have numbers on the door, starting with room 1, but they also have rooms with real numbers on them. And every real number between 1 and 10 has a room associated with it. So think of any real number between 1 and 10. 5.718365, there's a room number. There's a door with that number on it. And Blauman's Hotel is filled up tonight. And eventually they decide this is kind of lame, we want to go to Hilbert's Grand Hotel. So they all come across to the next town, and they go to the front clerk and they say, we would like to stay at your hotel, can you find room for us? And the clerk shakes his head and said, sorry, there's not enough space. And the reality is there is no way that you can do any of these little tricks and fit in all the guests from this hotel into Hilbert's Hotel. It's a fundamentally bigger infinity, the set of real numbers from 1 to 10, fundamentally bigger infinity than the set of integers going up without bound. And so in the language of cardinality, we can make the following statements. The cardinality of the integers is the same as the cardinality of the integers union, I don't know, the set of consisting of a smiley face, right? Which is the same as the cardinality of the even numbers, which is the same as the cardinality of the prime numbers, right? These are all infinite sets, they all have the same cardinality. But the cardinality of the real numbers is bigger than the cardinality of the integers. There's somehow more real numbers than there are integers in a very profound way. Whereas I could make a set consisting of the integers drawn in red and another set consisting of the integers drawn in green and another of the integers drawn in blue. And that collection of 3 sets has the same cardinality as the original set of integers. But somehow when you get to reals, you get a bigger set. So what about fractions? What about the set of rational numbers? So this is a set of all fractions, a over b, where a and b are integers. So it's kind of like an infinite number of these infinite sets of integers. And it turns out the cardinality of this is exactly the same as the cardinality of the integers. And it's really easy to demonstrate that. And the demonstration of that gives us a clue to the nature of the set of integers. So let's just think about fractions m over n. And I'm going to draw m going across and n going down. And on each axis, I'm just going to list the integers from 1 on up. And I'm only going to worry about positive numbers for now. But we know if we can say something about the set of positive elements, we can say the same thing about the positive and negatives together, because we're just doubling the number of elements. So I'm going to write down the fraction corresponding to this m and this n. So this is 1 over 1, this is 2 over 1, 3 over 1. And the second row is 1/2, 2 halves, 3 halves. And I'm not going to do this too far, because I'm about to make a really big mess on this. And so on. Okay, so first question, any rational number bigger than 0, is it going to appear somewhere in this table? It's got to, because a rational number by definition is a ratio of 2 integers. And if it's positive, both of those are positive. And if I just move across m spots and move down n spots, that's where the number m over n will be. So any rational number is going to appear in this table eventually. And it may appear more than once. In fact, it's guaranteed to. Because 3 over 2 is going to also appear as 6 over 4, and 9 over 6, and so on. So this collection of numbers has all the rationals in it multiple times. In fact, an infinite number of times. But we can prove that this is the same size as a set of integers. Even though this is multiple copies of the rationals, it's the same size as a set of integers. And the way we do it is by traveling through this set of numbers. So I'm going to start here. I'm going to move over. I'm going to move backwards on this diagonal. I'm going to move down, and then up a diagonal, across, down a diagonal, down, up a diagonal, and so on. So the next thing I'll ask you to believe is that following this path, I will eventually hit any particular number that you choose. I will never hit every number because this path is infinite in length, but you pick any number, 45 over 319, eventually I'm going to draw a line through it. And this path gives me my mapping between the integers and the rational numbers. And so the integer 1 I'll associate with this, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and so on. And I could throw out the duplicates and just skip over them, and it gets even easier. But the punchline is, this big set of fractions I can put into one-to-one correspondence with the set of integers by just counting them in this particular order. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And so the term countable, a set S is countable if the cardinality of S is the same as the cardinality of the integers. Why? Because if it's got the cardinality of the integers, it's got the cardinality of the positive numbers, positive integers, which means we can make this one-to-one mapping between positive integers and the elements of S, which means we can say this is the first element, the second element, the third, the fourth, and so on. So we can count these things, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So countable means cardinality of the integers. And integers, even integers, positive integers, integers bigger than 1,000,000, integers less than negative 17,005, prime integers, all of these sets have the same cardinality as the integers. And we have a symbol for this, which is aleph naught. And if you see that symbol actually drawn, it's a really beautiful Hebrew character. I never learned how to draw it very well. But it's aleph naught. The real numbers have a cardinality bigger than aleph naught. And we can prove that pretty easily. And this is an elegant proof. Prove that the cardinality of the real numbers is bigger than the cardinality. Did I tell you up front you don't really need to worry about this stuff for the exams?
I didn't sit.
All right, so how do we prove this? Let's do a proof by contradiction. So assume cardinality of R equals the cardinality of Z. Then we can make a one-to-one correspondence between the integers and the real numbers. Okay, so let F going from Z to R be a one-to-one correspondence. So you come to me and you say, hey, I proved that these have the same cardinality. I'll say, oh yeah, give me a function that gives a one-to-one correspondence between the integers and the reals, and you give me a function. Here's what I'm going to do. I'm going to take the integer 1, and I'm going to write down next to it the real number corresponding to 1. Well, maybe that's good old pi. And I'm going to take the number 2, and your function's going to give me another number, maybe that's e. And you give me the number 3, and maybe that gives me the real number 0.50000. And I'm going to keep doing this. And I'm going to make a table, infinite table, and the nth entry is going to be the real number corresponding to n. And now I'm going to construct a new real number. I'm going to call this b for bad. And here's how I'm going to construct b. The first digit of b is going to be the first digit of this first number plus 1. So this is going to be a 4. I'm assuming I'm just looking at numbers from like 0 through 10. Okay, the second number of b is going to be the second digit of the second number plus 1. The third digit of b will be the third digit of the third number plus 1. The fourth digit will be the fourth digit of the fourth number plus 1, and so on. And if one of these digits happens to be 9, when I add 1, I'll just write down a 0 instead of a 10. So I end up with a number. It's a real number, but it cannot appear anywhere in this table. And how do you know that? Because suppose that the number 55 is supposed to map to this number. Well, the 55th digit of this number and the 55th digit of b are not going to be the same. Because the way I constructed b was to take the 55th digit of this number and add 1 to it. And that digit's going to be different. And it doesn't matter if I pick the 55th number or the 17th number or any number. Any number that you pick out of this table is guaranteed to be different from b, which means b is not in this table, which means in this mapping that you gave me, there was no integer that mapped to b. And so you don't have a one-to-one correspondence. So assuming that these have the same cardinality always leads you to a contradiction. And therefore, the cardinality of R is bigger than the cardinality of Z. So that's a diagonalization argument, and it's named diagonalization because you're going down the diagonal and sort of wrecking things as you go. And that's another version of Russell's paradox, as I mentioned the other day. And this has some interesting consequences for our lives. So how many C programs are there?
7.
7. Once you've written them, you don't have to take classes anymore. There's definitely an infinite number of C programs, right? But is it the same cardinality as the integers? Assuming that every C program is finite in length, which it has to be, well, it's really just a big long string of ones and zeros. That's just an integer. So every C program can be turned into a single really big integer. And every integer can be turned into a C program, although most of them won't compile. But even though there's no limit to how long a C program can be, it kind of by definition has to be finite in length, if you're going to compile it at least. So the set of C programs has the same cardinality as a set of integers, which means there are more real numbers than there are possible C programs. So that might mean there's real numbers you can't print out with a C program, no matter how good a programmer you are. Or rather, if you write C programs that print out a single real number, there's some numbers you can't print out. So that's a little weird. We haven't gotten to the good stuff yet. We got 5 minutes left. So the cardinality of the integers is what we call aleph naught. And we know the cardinality of the reals now is bigger than the cardinality of the integers. But trying to get from here to something bigger was a little hard. Adding an element, adding 2 elements, adding the same infinite set of elements, adding the same infinite set of elements in rational numbers, we still got stuck here. But when we went to reals, suddenly we jumped up to something bigger. So here's the question. Is there a set H such that cardinality of H is bigger than the cardinality of Z, and cardinality of H is less than the cardinality of the reals? In other words, is there a set in between the size of the integers and the reals, bigger than the integers but smaller than the reals? Let's say again?
Yeah.
Yeah? Cool. We'll find out. Okay, so there's a famous hypothesis. It's called the Continuum Hypothesis. Which is sometimes just written CH. And CH claims no. The continuum, which is another word for the real numbers, is the smallest set that's bigger than the integers. That's what the continuum hypothesis claims. But it has not been proven. So, over here is the idea that the continuum hypothesis is true. Over here is the idea that the continuum hypothesis is false. So if it's true, it means there's nothing in between Z and R. So show of hands, how many people think continuum hypothesis is true? Nothing is bigger than Z until you get to R. And it's free to vote. There's no penalty. Oh, poor CH. Okay, we got 1. We got 1. Wow, people don't like CH. Okay, how many people think that it's false? Whoa, infinite number. Math by democracy. All right. So you said continuum hypothesis was true.
Well, I mean, it's the first 2 letters of my name, so if you're almost giving my name.
Excellent.
Be in favor of it.
Guess what? You're not wrong.
I'll take it. I'm not right either.
Everybody else, you're not wrong either. Continuum hypothesis cannot be proven, nor can it be disproven. It's what's called formally undecidable. And, annoyingly, it's been proven that CH is undecidable. People who think about this stuff have proven that it is impossible to prove or disprove the continuum hypothesis. It's a gap in our system of mathematics and logic. It's this little spot where there's a statement that's really easy to state, 20 minutes worth, and you can never find a proof for it, but you can never find a disproof of it either. It's undecidable. And it's one of those things that Gödel warned us about in the incompleteness theorem, that if we don't have paradoxes in our set theory, we're going to have undecidable propositions, things that can't be proven or disproven, and this is one of them. And that's weird and hopefully disturbing. So if you didn't lose yourself looking up axiom of choice, look up continuum hypothesis and have some fun with Wikipedia and see where that leads. All right, last two things. One, I'm going to post your next homework tonight. That'll be due a week from today. Two, how many people are going to be upset or heartbroken if I cancel our quiz 1 for Friday?
Danny, raise your hand. You love quizzes.
Okay, because we missed like 4 or 5 days between strike and holiday and 2 medical things with me. So I'm going to cancel quiz 1, and we'll just do quiz 2 at the usual time. But I want to concentrate on homework and going through the next material. All right, so I will see you next time.